Very good morning to all of you. Today I want to start Module 3, Session 7. Title of Module 3 is Lateral Earth Pressure. For this lateral earth pressure, our course outcome is ability to compute lateral pressure distribution behind earth retaining structures. So this is the course outcome of this lateral earth pressure. Title of subject is Geotechnical Engineering and subject code is 18 CV62. It comes in 6th semester of Civil Engineering Department. Now see lateral earth pressure explanations in terms of active earth pressures. So last sessions we have discussed about Rankine's active earth pressure concept. So now I want to explain about how to determine lateral pressure and how to plot the pressure distributions based on active earth pressure. See here. Okay. See, this is the explanations. So this is the height of the retaining wall of H1, H2, two layers, and here surcharge pressure load is given Q in kilonewton per meter square, and here water table at a depth of H1, and here this is H2. Water table is acting at a height of H1. Below its backfill property is given gamma saturated 5C. So these are the properties of backfills. Now based on these conditions, how to plot the active lateral earth pressure for a cohesive backfill with surcharge. Earlier we have discussed lateral earth pressure for sandy soils. Now we are discussing about cohesive soils. Okay. And now how to plot the pressure lateral earth pressure diagrams based on this case. See here, this pressure distribution diagrams. So from this you draw the rectangle distribution diagram. This is based on Ka into Q, and from this is triangles. So this diagram is based on H1 into gamma into Ka. So means this total pressure at the base at a height H1 is Ka into Q plus Ka times H1 into gamma. Here H1 into gamma means pressure, height into unit weight of soils. Okay. And for this layer, second layer, so pressure distribution we are calculating based on active earth pressures, that is sigma A is equal to this pressure plus this pressure. So here see, this is KAQ plus KA H1 gamma is this, plus this pressure distribution diagram, that is Ka times H2 into density. Here below the water table means density is gamma submerged. Gamma submerged is nothing but a gamma saturated minus gamma W. So this is the lateral earth pressure due to layer 1, layer 2 with surcharge. Okay. And this is the active earth pressure you deduct. So this is 2C times root Ka. Okay. Then you deduct add what pore pressures. So pore pressures at a depth of H2 is given height into unit weight of water, that is H2 into gamma W, this at the base. So then finally we are getting active earth pressure for this retaining wall is given based on this value. So here see here at the top Ka into Q minus root 2 times C root Ka, and here this is sigma A dash, that is active earth pressure, is we are getting KQ plus Ka into H1 gamma minus 2 times C root A. You deduct this value. Okay. And here is also this minus this plus this. So here, so this means this pressure. So here KAQ plus KA H1 gamma plus KA H2 into root of gamma saturated minus gamma W minus this 2C root KA plus this pressure, that is H2 into gamma W. So this is the lateral earth pressure with respect to active is given. So this technique you should be remember. But here we are calculating lateral earth pressure at the base with respect to given condition is we are calculating with respect to height into density of soil multiplying coefficient of active earth pressures. This is the simple calculations or logic. Okay, so that is explained here clear. Figure 7.211a shows a retaining wall supporting a field with a water table located at a distance h1 below the top surface of the field. A uniform pressure Q is applied at the top surface of the backfill. The wall is allowed to move away from the soil, thus mobilizing the active earth pressure. Let us assume that the soil below the water table is fully saturated. The distribution of the effective lateral earth pressure and the poor water pressure are shown in figure 7.11b. Means see here this and this. Okay, at depth z equal to 0, so active earth pressure is given KAQ minus 2C into root Ka, and pore pressure is U equal to 0. So at depth z equal to 0, so this pressure, okay, this pressure at a depth z equal to 0, and at a z equal to h1, so the active pressure is this, that is this at a depth z1, that is KAQ plus Ka times h1 gamma. So here KAQ plus Ka h1 gamma minus this active pressure. So this is, that is 2C root Ka, and U equal to 0, that is pore pressure. At z equal to h1 plus h2, it became h. So then we are getting, so calculating here, sigma dash h is KAQ plus Ka times gamma h1 plus Ka times gamma saturated minus gamma W into h2 minus 2C root Ka. So these equations at the depth h1 plus h2, and U equal to height into density, that is h2 into gamma W. So this is the calculations or logic of how to calculate lateral earth pressure at the base of the retaining wall, at the hill. To calculate the lateral force, we can simplify the pressure distribution using triangular and rectangular shapes as was done in example 7.1. Earlier we have done. Same logic is applied here. The area of each shape can be calculated separately to give us the lateral force that must be applied at the centroid of the respective shape. The sum of these lateral forces is the total lateral force exerted on the wall. The point of application of the total lateral force can be calculated by taking the sum of the moment of all forces about the hill of the retaining wall and equating that to the moment of the total lateral force about the hill. So we are getting centroidal distance, similar to problem 7.1. So this is the explanation about how to determine force. Okay. Next, Coulomb theory. So let us see Coulomb theory. The Coulomb active earth pressure theory assumes that a soil wedge with a failure plane making a critical angle theta CR with the horizontal is in a condition of incipient failure as shown in figure 7.12. Okay, see this is figure 7 point. This Coulomb active lateral earth pressures. Okay, so this is the retaining walls. Okay, and this is the backfields, and this slope is acting at an angle alpha, that is ground surface acting at an angle alpha, and this is self phase of the backfield, and these are the how normal force and shear force are acting. Okay, so this P we are locating at an angle delta, and here this retaining wall we are plotting at an angle beta, and here this due to wedge. Okay, this resisting force R is acting perpendicular to the backfields, and this resisting force is we are locating at an angle phi dash. So then this concept we are locating here theta versus P value, and here this is the critical angles, and these are the total force P equal to active earth pressure PA. So P equal to PA. So here where there is a tangential point, so this is the our dP by d theta is equal to 0. So then theta becomes critical theta and P becomes PA, that is active earth pressures. This is the Coulomb active lateral pressures. The intact wedge is about to slide down the failure plane, thus generating active earth pressure against the retaining wall. From statics, the wedge can be treated as a particle that is subjected to three coplanar forces W, P and R, where W is the self weight of the wedge, which can be determined easily by multiplying the area of the wedge with the unit weight of the backfield. P is the resultant of the wall reaction against the soil, and R is the soil reaction against the sliding wedge. The force P makes an angle delta with the normal to the back face of the wall. The angle del is the wall soil interface friction angle, which can be determined from laboratory tests or can be assumed as a friction of phi dash. Usually you can assume that del equal to 2/3 phi dash. The force R makes an angle phi with a normal to the failure plane. The internal friction angle phi is assumed to be mobilized at the interface between the sliding wedge and the underlying soil. Okay, means it is to be noted that in Coulomb theory, the backfill soil is assumed to be failing only along the failure planes. Backfill soil is failure only along the failure plane, whereas in Rankin's theory, every element within the backfill soil is on the verge of failure, as discussed earlier. Also, Coulomb theory accounts for three factors that were not accounted for in the original Rankin's theory. The wall soil interface frictions signified by the friction angle del in figure 7.12. The sloping backfill soil with an angle alpha and the battered back face of the retaining wall with an angle beta. So here this is the figures 7.12 and this figure is explains. Okay. As shown in figure 7.12, Coulomb theory considered a trail wedge with a failure plane making an angle theta with the horizontals. Making an angle theta with the horizontals. Okay, these are the theta. Okay. At failure, two equilibrium equations can be written, that is along the x and y axis, assuming an impending motion condition, that is the wedge is about to slide down the failure plane. Those two equations involve three unknowns P, R and theta, we need a third equation involving sum of the three variables to solve for the three unknowns. Note that P, W and R will vary if a different angle theta is used. Coulomb theory searches for the angle theta equal to theta CR, that is critical conditions, that yields the maximum earth pressure P equal to PA. Thus, dP by d theta equal to 0, this is equation 9. So then the solution of equation 7.9 will yield the angle theta CR, that is critical angles. And subsequently the corresponding maximum earth pressure PA, that is maximum active earth pressure PA, can be calculated. Let us consider the simple case shown in figure 7.13. This is figure 7.13. Coulomb active lateral earth pressure for a frictionless vertical wall and a horizontal backfills. So this is retaining walls, and here wall is horizontal, top surface is horizontal, that is alpha equal to 0. So here W, we are this is the self weight of the backfill ejecting downward, and here del is 0, then P ejecting at the horizontal, and this is the force we are locating at an angle phi dash, and this with respect to theta minus phi dash. Okay, so this is the wedge concept, and here we are calculating W equal to gamma h square by 2 times tan theta. Okay, so according to figure 7.13, in which the retaining wall has a vertical back face, that is beta equal to 90 degree, with a frictionless surface del equal to 0 and a horizontal backfill soil alpha equal to 0. Note that these are the assumptions used in Rankine's theory, and the following Coulomb solution can be compared directly with the Rankine's solution described in above sections. The height of the wall is h, and the friction angle of the granular backfill soil is phi dash. Here C becomes 0. Consider a wedge with an angle theta as shown in figure 7.13. The closed forced triangle shown in the same figure indicates equilibrium of the wedge that is on the verge of failure. The weight of the wedge is function of the angle theta as follows, that is W is calculated gamma h square by 2 times tan theta. Okay, this diagram is explained based on this sketch. Okay, for horizontal and vertical equilibrium respectively, the following equation must be satisfied. Here P equal to, while resolving, P equal to R sin theta minus phi dash and W equal to R cos theta minus phi dash. Substitute equation 7.1 into 7.12, then we are getting gamma h square by 2 times tan theta equal to R cos theta minus phi dash. So dividing equation 7.11 by 7.13, we get P equal to gamma h square by 2 tan theta into tan of theta minus phi dash. Then combining equation 7.9 and 7.14 yields dP by d theta equal to 0. So then theta equal to critical theta is equal to 45 plus phi dash by 2. Then substituting equation 7.15 into 7.14, it becomes active earth pressure PA equal to gamma h square by 2 into tan square of 45 minus phi by 2. But for a granular backfill, the active force PA is given by PA equal to Ka into half of gamma h square. So then substituting equation 7.17 into 7.16, we get Ka equal to tan square of 45 minus phi by 2. Active pressure coefficient is given Ka equal to tan square of 45 minus phi by 2. Equation 7.18 is identical to equation 7.6, which was obtained from Rankine's theory, that is K equal to 1 minus sin phi by 1 plus sin phi. The Coulomb active earth pressure coefficient for the general case shown in figure 7.12 is a more complicated expression that depends on the angle of the back face of the wall, the soil wall friction, and the angle of backfill slope. So K is given by these equations, that is sin square of beta plus phi divided by sin square beta into sin of beta minus del into bracket 1 plus root of sin of phi plus del into sin of phi minus alpha by sin of beta minus del into sin alpha plus beta wholes. This is equation 7.19. You remember these equations, Ku. Okay. Then these are the references or refers to cover the session 7 of module 3, that is lateral earth pressures, to cover in details. Okay. Thank you one and all. Next class I will be continue.